Chinese teachers I
Leo takes every teacher's ID. Blue boy.
I only follow the one I didn't say. Show me.
So beautiful.
40.
These are just
Hanging off of his here on like no I want to say
Yo, blue boy. Blue boy.
Let's say rainbow.
Rainbow boy.
5 stars.
I see me over here. I can see my face.
Sure.
Don't worry, yours next year.
Exactly. Right. Oh, Athena. Because of you guys, Miss Arvina will not do the mock test today. Do it first. I thought it was
Very quick, just until 60%.
Yeah, that's why I came half day.
Number 15.
That's why I didn't come in. But she thought that you guys will not go for the whole day. You said like half a day.
24.
Oh, she has been absent.
Yeah, 4.
15 days now. Don't worry, this is why. And I think for the other lesson, the IT will arrange Zoom lesson. Yeah, like Zoom lesson. So to be able to. Because if I use Zoom, I don't know how she's doing.
Only Zoom for. Yeah, I think so because she has like. She's been told to rest the 4th of November.
Does she know the code?
No,
On Zoom lesson.
Very minor.
no, really. She's going to
Oh, Janet? Yeah. Oh.
No, she's
Jeanette! Is that Jeanette?
Oh, is that?
I don't know. Control.
Yeah, that's right.
Is that you?
That's
You guys can might have her like.
Is that Janet? I can't see.
It's 667 30621. Yeah, so 667.
Is that Emily?
No.
No, isn't there?
Testing. Okay. Right, 667 3062184. Okay,
So long.
and see if she can join
So
in. Right. Six six seven 3062184. If she is not free right now, I can just upload the video. Yeah, she's dancing, yeah, and then she can join. So 667 3062184.
in the password.
219. Right. Okay, so then. Okay, let's pick up from where we were, okay, and let's just wait for her for a bit. So yesterday we stopped at like the introduction of the different like periodic trends, okay, and we said there are trends in many different properties like melting point, like electrical conductivity, and then the oxides, okay. So we'll look at that now. But any question from yesterday first?
No.
No, okay, right. So we'll pick up from the melting point discussion. Okay, so melting point. So if she can't join, like let me know. Okay. So this is the melting point trend that we'll look at next. So which group of elements do you think has the highest melting point of the entire period? If we consider just one period as an example. So consider period 3, okay, as an example. Similar argument applies to other periods. Okay, but let me just put down Na, Mg, Al, Si, Ps, Cl, and finally Al. So these are period free elements. So as we go from left to right, how do you think the melting point will change? Or maybe let me rephrase the question, which element in period free do you think has the highest melting point and why?
Na.
You think it's Na. So you think it's Al. Actually Al is the lowest rather than the highest. Silicon instead has the highest melting point. Okay, so can you help me sketch the melting point trend first? So this is melting point up on top, and the x-axis is just the atomic number. So we have atomic number from 11 all the way to 12, 13, 14, 15, 16, and then we have 17 and 18. Okay, so these are the atomic numbers. So I'll just put the first and the last one, and then you know the rest. So the melting point peaks at silicon. Okay, so put the highest melting point in here. And then it will rise from sodium all the way to aluminum. Okay, and I'll ask you the reason. Okay, so help me sketch this first. And then it will fall back down, okay, to phosphorus and rise a little bit at sulfur. It will fall back down again at chlorine and argon. So we see this melting point trend in here. So there are two things we can learn from this diagram here. Number one is that we can use it to divide elements into 4 types. Okay, so can you help me draw 3 dotted lines here to separate these elements into 4 main types of structures. Okay, starting with Al, Mg, and Na. These are known as the metals. So Na, Mg, Al, they are known as the metals. Then we have Si at the middle. Okay, so this is Si. It has like a giant covalent structure, which is maintained by many strong covalent bonds. So this is why it peaks as Si, as silicon. And then when you see the melting point will fall back down to phosphorus, sulfur, and chlorine. So these are the non-metals. But you may not know this. Phosphorus and sulfur, they are like a non-monoatomic, okay? So they are polyatomic. Does anyone know what the formula is for chlorine? So everybody knows chlorine is Cl, but what is the atomicity? Meaning Cl2, yes, Cl2. Sulfur and phosphorus have, P4 and SA. These are the atomicity, okay? If you don't remember this, you might need to review the Form 4 textbook, okay? Atomicity is the number of atoms in a molecule, okay, of each type. So some molecules, like chlorine, as you have learned, they are made of 2 atoms only. Some other non-metal atoms, like phosphorus and sulfur, they will have different atomicity than 2, okay? And what do we call these structures? These are simple covalent molecules. And finally, you notice that I left out argon, okay, but that's on purpose, okay? That's because argon, it doesn't even form molecule. It is a simple atom. It is just a noble gas, okay? It does not form molecule. So we will be able to, is she able to get in? Okay, because I see nobody entering the meeting here. Yeah, and I wanted to maybe expand it a little bit. Okay, so I will still be able to see it from here. So can you put down these 4 types, okay, and write down 2 key points we can note here. So note number 1, silicon has the highest melting point. So it has the highest melting point in a period, okay, in period free. And how do we explain that? Well, we say it forms a giant covalent structure with many strong covalent bonds. Okay, does anyone know how to draw the structure of silicon? When we say silicon form a giant covalent structure, it has the same, or I should say similar giant covalent structure to which substance? Diamond, yes. Okay, so can you draw this? So you have carbon or silicon. Okay, they all have same structure. Okay, so carbon in the structure diamond or silicon, they have the same structure. Okay. Oh yeah, like just if you can't, she can't join. Okay. Then maybe you mean she couldn't join the Zoom chat because of the login error, or she is occupied right now. Okay. Okay. Then she can refer back to the video later. I'll upload it. Okay. For Janet. So let me just close this first. Okay. Then we have draw the structure here. Okay. If you have trouble drawing it, just draw a tetrahedron. You know this is a tetrahedron, and then just copy and paste it. Okay, then you'll be able to draw the rest. Okay, you see this is another tetrahedron, another tetrahedron, another tetrahedron. So this is the giant covalent structure. So explanation point number one is that Si has a giant covalent structure with many strong covalent bonds. Okay, you see these are strong covalent bonds. If you want to release just one of the Si atom, you need to break 4 bonds. Just think about it. Releasing one Si atom requires the breaking of 4 strong covalent bonds. And this just for one Si. You have many Si in silicon. That will take a lot of energy just to melt it. So with many strong covalent bonds, you must then say this requires a lot of heat to overcome. Okay, so this means a lot of heat is needed to overcome these strong bonds. Okay, you can't miss this point. A lot of students jump from the second point to the last point and they say, oh yeah, they have many strong covalent bonds and so high melting point. No, you have to add this orange sentence in between and say, well, if they are strong bonds, then it will mean a lot of heat is needed to overcome them. Okay, which finally explains why they have high melting point. Right, that's the first thing you should take note of. Okay, the second thing you can take note of is metals. They have the second highest. Okay, so we can group them together. They are just below silicon. The molecules, they have the third highest. And finally, atoms, they are the lowest. Okay, so put this down. When we are to classify things, okay, we have giant covalent structure to have the highest melting point of all the elements, followed by metals, followed by molecules, followed by atoms. Okay, so molecules, and finally we have simple atoms. We'll look at each of these classes, okay, individually. So starting with, so you can put down the melting point order. So this is the melting point. Giant covalent structure, they have the highest. So the green thing in here. The metals, they have the second highest collectively. Okay, you see these 3 points sit between the giant covalent structure and the simple molecules. Then we have the simple molecules, and finally the simple atoms. Okay. We've just explained why giant covalent structure has the highest melting point. What about the metals? Why do we see this sort of trend here? Why is Na having a lower melting point than Mg, which in turn has a lower melting point than Al? So here's the third point. So put this down first. Point number 3. We then explain the melting point trend in metals. Can you tell me what is the name of the bond found in metals? Metallic bond. Okay. Do you know what metallic bond strength depends on?
Size.
Depends on the number of electrons delocalized. How many electrons does sodium give up as it forms ions?
1.
1. What about Al?
2. 3.
Al?
3.
3. Mg will be 2. So can you put down this proportional relationship here? Metals have metallic bond, and metallic bond strength depends on the number of electrons each atom delocalized. Okay, so metallic bond strength is proportional to the number of delocalized electrons. In other words, the more electron delocalized, the stronger the metallic bond. So you all should know this symbol, proportional to, okay? And let's put down how many electrons does each of these elements give up. So we have over here, so we have Na. Na will become Na plus charged ion. In the process, they will give up one electron. Let me draw that in blue, okay, so that you can see, well, in metal, we have ion and electrons, like that. But then with Mg, you have Mg2 plus charged ion. And every time Mg2 plus ion is formed, it will give up 2 electrons. So you have something like this, so you see more electrons now. And finally with Al3 plus, every time Al3 plus forms, there will be 3 electrons given up by each Al atom. So that means there is a lot of electrons, delocalized electrons in here. So these are the number of delocalized electrons. In other words, the metallic bond strength goes in this order. Okay, Na has weaker metallic bond than Mg, which has weaker metallic bond than Al. In other words, Al has the highest melting point. Okay, so write down strongest metallic bond on the right, weakest metallic bond on the left. So this explains the melting point trend of just this part. Why does it follow an increasing trend in here? Can you see this pattern? This rectangle, okay, explains only this trend, only these 3 dots. It doesn't explain the other dots. This single dot is explained by the giant covalent structure of Si. Okay? So far so good, right? Now we'll turn our attention to the right-hand side of this graph. Okay, we dissect this graph into several parts, okay, to study it. So write down metallic bond. Now we look at this part. Let me draw a box here first. So we can explain the metal trend using this rectangle. What about the molecules? Does anyone remember the name of the interaction found between molecules? When the Wells force. Okay, when the Wells force. So can you draw, I hope this is not too distracting. Okay, let me draw another box around here. And can you write down the melting point trend in molecules and atoms? Okay, we'll discuss molecules and atoms together. Okay, so and atoms. So we have phosphorus, sulfur, chlorine, and argon. Okay, so you have P4, S8, Cl2, and Al. These on the left are molecules, but this single one on the right is an atom. Okay, it doesn't even form a molecule. And when we draw out the atoms, you see P4 looks like this. Okay, it is a tetrahedron. It has a tetrahedral structure, just 4 phosphorus atoms connected this way. Okay, so 3 bonds from each phosphorus atom. Sulfur is a little bit harder to draw, but if you know how to draw a crown, you know how to draw S8. It has a crown shape, we say. So write down the name. This is tetrahedral. Phosphorus is tetrahedral, a molecule. S8 has a crown shape. It's a crown-shaped molecule. And Cl2 can't be any simpler. It's a linear molecule. It's a straight chain. So it's a straight chain. So linear molecule. And finally, we have argon. Argon is lonely, but it's fine. It's actually quite comfortable with being lonely because it's already stable. All the other molecules, they need to form some kind of a bond because they don't obey octet rule by themselves. They need to form some bonds with other molecules to gain stability. But then when the Wells force, as you may recall, depends on the size of molecules. So can you draw another purple box in here and write down molecules and atoms they have in between them when the Wells force. So molecules and atoms have in between them when the Wells force. So this is a keyword. From this point onward, I'll write VDW. Okay, so to represent when the Wells force, but you should write it in full in exam. So you have atoms on the right, molecules on the left. They are when the Wells force. And when the Wells force strength depends on the size of the molecule. The bigger the molecule, the stronger. So you see this proportionality relationship. It depends on, metallic bond strength depends on only the number of the localized electron, at least in this level. When the valence bond strength depends on the size of molecule. So which of these molecules is the largest? S8. Okay, yeah, I don't even have to give you the relative atomic mass because you can see for neighboring elements on the periodic table, do they have similar or very different relative atomic mass? Neighboring atoms, very similar. So that means I know there's a difference in the relative atomic mass, but what is more important, you see, is the atomicity now. Okay, this is 4 times the relative atomic mass of P, 8 times the relative atomic mass of S. That means, can you now arrange these 4 things in increasing order of size? Which is the smallest? AR, followed by Cl2, followed by P4, followed by SA. Which is why you now can explain things. Okay, this is P4, so it is the smallest. Argon is the smallest, followed by chlorine. Chlorine is the second smallest. P4 is the third smallest, or the second highest. Among these 4. Okay, and finally you have S8. So now we can explain every aspect of this graph. Okay, so is everything crystal clear about the graph first? Yes, you need to draw this graph, unfortunately, in the exam. Okay, so this is the number, right now, or I should say size of molecule. And after we rearrange them in ascending order of size, so in ascending order of molecular size, okay, so molecular size, we have argon smaller than Cl2 smaller than P4, okay, which is in turn smaller than S8. So therefore, this has the lowest melting point of all 4, and this has the highest. Okay? Right. And the nice thing about the periodic table is that you don't just see this trend in period 3. You see this in any other period. Okay? So which is why now we will zoom out a little bit and we look at the other elements as well. Okay? So finally, at the bottom here, can you help me draw this? Okay. So you have highest and lowest boiling point and melting point in here. Here. You can write melting or boiling point, doesn't really matter. Okay, in here, so melting point. And then we can draw the periodic table. This is not a periodic table, but the atomic number here. You have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Maybe for this part you don't have to copy, okay, because you will find this on the textbook. And I don't think they will ask you to draw this graph. I just want to use this to prove a point that there is periodicity. Periodic changes you see happen over and over across periods. Okay, so you have F, Ne, Na, Mg, Al, Si, P, S, and then you have Cl, Ar.
How the hell do you know that?
If you ask me anything beyond Ar, I don't remember, trust me.
It's just up to 20.
Yeah, up to, for DSE you only need to know up to 20. And it's not the order that you need to memorize. Why memorize? You have the periodic table. Do you have too much memory in your brain? Okay, no. Okay, don't waste time memorizing.
Why are you memorizing?
Well,
Waste
because
your
I need
time.
to, because I don't want to keep referring to the
He's a
periodic
teacher,
table.
we're students.
I just want to remember it. Okay. So can you put down melting point? What we are seeing here are 3 different periods. Can you put down period 1, period 2, and period 3, which we just discussed? Okay, we can zoom out a little bit. Zoom out a little bit. This part would fall in here. Okay, so can you copy this? Okay, so you have so it will rise up and then it will do something like that. In the other period, you see the same thing. So for hydrogen and helium, there will be a rising trend. That's because which of these is has a larger mass?
Helium?
Helium, yeah, because this is actually H2. If you want to write down the real formula, this is H2, okay, and then this is N2O2. If you have to guess, most nonmetals are diatomic. Most, not for phosphorus, sulfur, and phosphorus and sulfur. Most nonmetals are diatomic, except the noble gases. Yeah, and then you will see another trend in here. 4 usually. Yeah, because why does it peak at group 3 and 4 for period 2 instead? That's because boron also has a giant covalent structure, not just carbon. Okay. Yeah. So maybe we can use the same color. Yeah. Or if you don't have colors right now, you don't have to do that now. So these have giant covalent structure. This one have giant covalent structure, which is why this is where the graph peaks. Okay. Most likely this will appear in MC. So you have the metals here. So metals, when there's an increase in the number of delocalized electrons, you will see an increase in melting point. So you see beryllium is 2 plus charge. Li is 1 plus charge. So no wonder beryllium has a high melting point than Li. This one we already saw. And then we have molecules here. So these are molecules, these are molecules. Do you see what is happening? A periodic trend that repeats itself from one period to the next. Okay, so you have period 3. You don't have to memorize all 7 periods. There are 7 periods on the periodic table, but what you learned in this part of the page, okay, you can extend it onto other periods as well. So it's this part on melting point cleavers. Okay, so now we look at the next trend, which is electrical conductivity. Okay, so
how many trends are there?
Oh, yeah, I don't mean to scare you. This is actually the entire periodic patterns in the periodic table. Yeah, so these are all the statements in this chapter. Yeah, okay. But you know the other statements, they are explained in a very similar manner. Okay, let's take a look at electrical conductivity next. So we have electrical conductivity. When we study elements, we can divide elements into 3 main types. Okay, so elements, we call it periodic table of elements. They can be divided into 3 main types. One is called the metals. Okay, so you have metals. Metals, they are good conductors at any temperature. Okay, well, for those doing physics, the conductivity decreases with temperature because of the increased resistance. Okay, but we don't study resistance in chemistry. So we'll just say for metal, they are good conductor, generally speaking. Yeah, they conduct electricity, obviously. And then we have something in between, the semi-metals. So semi-metals are special. They have low conductivity at low temperature. Okay, at low temperature. But then when you raise the temperature, they conduct better. Okay, but higher conductivity at higher temperature. So we can explain it, okay, in DSE. So let me put down the explanation for why metals are good conductor first. Okay, so the explanation here is because they give up their delocalized electron easily. Okay, so they give up their outermost shell electron as delocalized electron easily. So as delocalized C of electron easily. For example, this is Na. So Na has 2, 8, and 1 electron. This last shell in here is the outermost shell. So it has 1 electron here. So this is the outermost shell electron. So this is the outermost shell electron. It is willing to give it up readily, okay? And as it does so, okay, it will form a sodium plus ion, okay? And then there will be an electron on the side. Yeah, and if this happens, like for all the sodium atoms in a sample of sodium. So let's just say this is sodium. If this happens to all the sodium atoms in a sample, what you have is at the end a bunch of sodium cations and accompanying it a delocalized electron. Yeah, so these electrons, they are free to move around. As you have learned in Form 4, when you connect this piece of metal, okay, so this is, let me put down Na. Na will become Na plus and an electron, right? Yeah. So when I do not apply a current through the metal, is there a net direction that the electrons are traveling? Do they travel in a particular direction when I do not apply a current? No, they move randomly. So let me copy this first. When you do not apply like a current, so here there's a switch, okay, and then you are putting the metal in here. So this is the metal which you put in here. However, as soon as you close the circuit, something happens. The electrons, they will flow in one direction only, okay, so you can see that as soon as you close the switch, the electrons will be heading from, oh, this we need to know, this is basic chemistry and physics. Show me where the electrons will be moving in the circuit when I close the circuit. From the,
Negative to positive.
so does it flow in this loop in a clockwise or counterclockwise manner?
Clockwise.
Clockwise, yes. So you will see the electrons heading this way. And as they move through your piece of metal, the electrons, they will all be headed this way, you see. Okay, before you close the circuit, they will just be wandering aimlessly. They don't know where to go. Okay, so they have no net direction before you close the circuit. But once you do, they will all move in one direction. This accounts for the high electrical conductivity of metal. Okay, so relates the good conductivity or the high conductivity of metal to the presence of delocalized sea of electron. Okay, right, so you have, this is Na here. When you look at a block of Na, you don't really just have Na atom. You have a lot of Na plus cation and the delocalized sea of electron. Okay, and this is the delocalized sea of electron that explains the electrical conductivity. With semi-metal, it's different. So semi-metal, they are kind of strange. They are a poor conductor at low temperature, but they are excellent conductor at high temperature. And the higher the better. Okay, let's see why. So this is silicon. Okay, so for example, silicon, yeah, it's a semi-metal. It has electron arrangement, I'll give it to you, is 284. So this is 284. It means it has 2 electrons in the first shell, 8 in the second, and 4 in the last one. So at low temperature, these electrons are bound very tightly to the nucleus. So they refuse to leave the atom, okay? So you have, let me write this in red. So this is the valence electron, or the outermost shell electron. So you have 4 outermost shell electrons. At low temperature, these electrons, they are bound tightly by the nucleus. So the nucleus at the center. But as you raise the temperature, these electrons, they will leave more readily, okay? So at low temperature, you can put down at low temperature, the valence electrons, or the outermost shell electron, are bound tightly by the nucleus. Okay, they cannot leave. And if they cannot leave, there will not be a delocalized sea of electron. And if there is no delocalized sea of electron, they are poor conductor. However, as you raise the temperature, increasing temperature increases the kinetic energy. So the electron will be able to shake off these attraction, okay, by the nucleus, and they can leave, okay, the silicon atom. So at high temperature, right? So at high temperature, the outermost shell electrons, they can leave more easily. So they can leave, right, more easily. So therefore, let me show you what it is like inside a silicon, like a sample, as I increase the temperature. So at first, you have a bunch of Si in here. Okay, at low temperature, you may just see 1 or 2 delocalized electrons around. So this is what you see at low temperature. Just 1 or 2 electrons here and there in the structure. But as you raise the temperature, at higher temperature, more electrons can leave the Si atoms, okay? So you will now have more electrons around. So therefore, which one has a high conductivity? At high temperature. So This is what makes semi-metals different from metals. And then we have the third category here, the non-metals. Okay, well, all non-metals except one non-metal, they are poor conductor, which is an exception to the statement that says all non-metals are poor conductor.
Graphite.
Graphite, yeah. So can you put down non-metals? They are generally poor conductor. Not the word generally, okay, because they are exception. The exception is graphite, okay. So generally poor conductor because they do not have the delocalized electron, as they lack the localized C of electrons, okay. And next to the word generally, write down graphite, except graphite. Graphite is unusual in that each carbon in graphite is bonded to how many other carbon? How many? You need to know how to draw graphite and diamond. So graphite has each carbon bonded to 3 other carbons. But knowing that carbon is a member of group 4, how many electrons does carbon have in the outermost shell normally? If it is group 4? 4. But then you see it is only using 3 of its electron in bonding. That means each of these atoms has actually thrown out the last or the 4th, okay, electron in the outermost shell. Okay, so put this important point down. Carbon is group 4, which means it should have 4 outermost shell electrons, right? So 4 outermost shell electrons. But then why is it that in graphite, why do we see such a high electrical conductivity? That's because each carbon, just look, each carbon has used 3 of its electrons in bonding. That means there's 1 spare electron that can delocalize. Okay? So right now, carbon use 3 of 4 electrons in bonding. So therefore, 1 electron is delocalized. What about diamond? Is diamond a good conductor or poor conductor? Poor. Now you also know why. Remember the structure of diamond or silicon we drew some time ago. You don't have to draw this again. I'll draw this for you. So this is diamond. Yeah, they have used, just take a look at one of the carbon. You don't have to look at all of them. Just look at one of the carbon and ask yourself how many bonds is it forming? 4. That means carbon has used 4 of its 4 electron in bonding. So no electron is delocalized. There simply aren't enough. There isn't an electron available. So 4 of its 4 electron in bonding. So no electron is delocalized. So now you can explain why only graphite is a conductor and diamond is an insulator. Okay? Is that clear? Right, yeah, I think we can show yourself for the bathroom break right now. Yeah, and when we are back, we'll finish the non-metal discussion. Okay? Yeah, or if you want to stay here, I can continue. Mobile. For this chapter, we are looking at elements only. We're looking at elements. So when you say mobile ions, they can only exist in ionic compounds, right? Yeah. So, but you're right. Things with ions, they can conduct electricity. But this chapter, if you look at the chapter again, it studies the periodic trends in the elements. Elements do not form ions by themselves. Okay, it's only when they form ion compounds that they form ions. Okay, so nobody needs to go to the break. I can continue.
No, wait.
Okay, yeah, then you can copy this first.
Come on, go to the bathroom. Go. So can you zoom in the diamond? Yes.
Right, yeah, you need to know how to draw graphite and diamond. I think graphite is much easier to draw. It just looks like a bunch of hexagons like in honeycomb. Diamond is difficult to take some practice. But really, you just have to know how many electrons are used in bonding. Is it free or is it full? That's what makes all the difference. And then with nonmetals, I think you can totally guess why nonmetals they are poor conductor. Because they don't have any delocalized electrons. Yeah, so in some way you see graphite is quite similar to a metal. In that, like metal, it has delocalized sea of electrons. Okay, but unlike metal, it doesn't form positively charged ions.
Why are there so many?
Well, you should ask the DSC exam board. I don't know why they are. Actually, if you combine all these together, they are, a lot. Yeah. You know, each section is really, really small, right? Yeah, each section, each topic is really small. But yeah, together this would be the periodic trends and patterns in the chemical world.
Were the scientists like
Yes.
discovering a lot of things like that?
No, I'm bad at physics, okay?
What electives did you take?
I didn't do DSE.
What?
I did
DSE?
ALE, HKCE and ALE.
Oh.
Long time ago.
Is it harder? Yeah, I think it's harder.
Before they were even HKDSE.
A-level was the one that Miss Choi and Mr. Kong took, I think. Right?
We used to have two exams instead of just one. Yeah. To some students, maybe they'll think, oh, having just one exam is better, right? But now, I think you will disagree. You're cramming everything into like Form 4, Form 5, Form 6. I used to have Form 7. When I was still a student, I need to do Form 4, Form 5, Form 6, Form 7. So what I used to study in 4 years, you guys have to study in 3 years. But they have trimmed a lot of stuff already. So it depends on how you look at it. Okay, yeah. But I still think it's better to have 2 exams for students. Yeah, it's too much in just one exam. And yeah, you either do very well or you're not even given a second chance. That's what I don't like about a single exam. But with 2 exams, if you did not do so well in CE, well, you still have a chance to catch up in ALE. Okay, but okay, let's focus on what's in hand, DSE. So non-metals. Non-metals, they are poor conductors because they do not have delocalized electrons. So you see the difference? Metals, they have a variable number of delocalized electrons. Group 1 has 1, Group 2 has 2, Group 3 has 3. For semi-metals, they have delocalized electrons, a different number of delocalized electrons depending on the temperature. So lower temperature means less delocalized of electron, yeah, and higher temperature means more. Okay, so they have variable conductivity. Okay, but then for non-metals, they do not have any delocalized of electrons except graphite. Okay, so except graphite. So therefore, non-metals, they are poor conductor. Okay, always. And so what does the conductivity look like in a period? So we'll just look at period 3. NaMgAlSiPsClAl. So these are non-metals. They have 0 conductivity. Okay, you don't see a carbon in here. So therefore, this exception does not apply. So I said except graphite. Graphite is a good conductor, but there's no carbon in here. There's no graphite in here. So they all have 0 conductivity. So can you put down conductivity here? This is 0. Okay? And silicon, they have, well, it's difficult to plot this. Okay, so you would just say it depends. Okay, so it depends on the temperature. So on the temperature. If this is high temperature, then it will be higher. If it's low temperature, then it will be lower. Okay? And for sodium, magnesium, and aluminum, which one has the highest conductivity? Aluminum, because it has the greatest number of delocalized of electron, right? So here we can really say, like it follows this trend, like that. Okay, but it's really difficult to plot silicon because it depends on temperature. Yeah, but then for these 4 points, it must be 0. Is that clear? Okay? Now we turn to some equations. Yeah, I know this explanation stuff bores you. Okay, so we now look at some equations. We have
So consider that in extremely high, will it still be higher than medium?
but that wouldn't be a fair comparison. Because you know when we do experiment, we need to keep temperature unchanged. So if you're talking about the same temperature, metals have high conductivity. But if you really have to push silicon to its limit, well, yeah, then maybe it can beat sodium. Okay, but yeah, I wouldn't compare it that way, as that's not a fair comparison. It's like asking apple and orange which one is better. Okay, there's no better. Okay. Now, next up we have oxides. Okay, so we are done with the elements. We now turn to the oxides. Okay, so we have oxide properties. Okay, so fortunately for oxides we only have to study period 3, but that's already a lot, as you will see. So consider the oxides, compounds of oxygen, formed by period 3 elements. Okay, so formed by period 3 elements. So we have, remember, Na, Mg, Al, Si, P, S, Cl, Al. Na will form the common oxide Na2O. Mg will form MgO. You can use crisscross rule here if you remember what that is. Okay, if you have a cation with an A plus charge and an anion with a B minus charge, you can just swap these numbers around, and then you can get the formula MbNa. Okay, so MbNa. This is what I refer to as the crisscross rule. If you don't call it that way, you don't even need to know the name. You just need to know how to apply it. Okay. So for example, why is the oxide of magnesium MgO? Why not Mg2O or MgO2? That's because Mg is from group 2, which means it has a charge of 2 plus. What about oxygen from group 6? Negative 2. And you know, you don't just swap the number, you need to simplify the ratio whenever possible. So 2 to 2 means 1 to 1. So 2 to 2 means 1 to 1. So you will then have just MgO. Okay, so how we get the formula, I'm not going to explain in detail, but you can refer to this rule. That's for the ionic oxides only. For the covalent oxides, unfortunately, you have to memorize it. Okay, so let me put this in here. Okay, well, so you have, for these three, you can explain the formula using this rule. So you have, what is the oxide of aluminium? So the formula of oxide of aluminum, Al2O3. Yeah, but for the non-metals or the semi-metal oxide, you have to memorize it, okay? So SiO2, P4O6, P4O10, SO2, SO3. You learn these two in the acid rain chapter. In the pollutant or acid and alkali chapter. And then you have Cl2O, Cl2O7, and for argon, good news, no oxide. It doesn't need to form oxide because it's stable. Okay, other things than noble gases, they need to form oxide because they wouldn't be stable by themselves. Okay, they aren't stable by themselves. So these are the oxides. And we'll look at a few features of these oxides, starting with their bonding characteristic. Okay, so can you move this? Let me move this further to the side first, and I'll write down bonding character or bonding nature. You know, bonds can either be ionic or covalent when it comes to compound. Maybe you're thinking, wait a second, haven't we learned metallic bond? Metallic bond is not found in compound. It's only found in elements, metallic elements. So this is why, when I say bonding nature, it can only be ionic or covalent here. So what do you think? How many oxides in here are ionic? How many are covalent? Up to which element? Up to Al. Yeah, so these are ionic oxides here. So ionic up to Al. And these are all covalent. So this has something to do with electronegativity, if you remember what that means.
No.
No, okay?
Something in polar bond chart.
Yeah, in the polar bond chart in microscopic world too, okay? So can you put down a short discussion, actually more like a recap on electronegativity? So recap on electronegativity. From now on, I'll refer to it as EN. So EN. So electronegativity is the ability of the atom to attract electron in a bond. So ability of an atom to attract electron in a bond. Let me ask you a question here. If you have two atoms, they are involved in a bond with a reference atom. Okay, so let's say I have two atoms in here for comparison. I have fixed this atom on the left, okay, so it doesn't change. What I'm doing is I'm changing the size of the right-hand side atom. Can you tell me in which case here will the right-hand side atom attract the electron in the bond more strongly? Is it when it is larger that it will attract the electron more strongly, or when the atom is smaller, they will attract the electron more strongly? Actually, it's when it's smaller, because the force of attraction depends on distance. So I like to imagine this as like the fridge door. This is like the magnet. When would the magnet be attracted more strongly by the fridge door? Is it when it's closer or when it's further? Closer. Okay. Yeah, I know this may not be a very good comparison here, because one is magnetism, one is electrostatic attraction. But anyway, you can see that if the nucleus is closer, it will be attracting the electron more strongly, right? So what is electronegativity again? It's the ability of an atom to attract electron in a bond. So what if I tell you that when you go from left to right on the periodic table, the atom, can you tell me how does the size of atom change across the period? It actually grows smaller. It actually grows smaller. So to your surprise, helium is the smallest atom, not hydrogen. You may think that hydrogen is the smallest atom, right? Do you? Yes, but helium is the smallest atom because helium has 2 protons. Hydrogen has 1 proton. Meaning helium with 2 protons, it will attract the outermost shell electron more strongly than hydrogen. Okay? Yeah, so can you put down the size of the atom? So this is in terms of size. What about electronegativity? If electronegativity and size, they are inversely proportional. Because with a small atom, it will attract the electron more strongly. So stronger attraction. The smaller the size, the stronger the attraction and the higher the EN. Can you show me what the trend is like for EN then? It will be the reverse, right? It will be the reverse. Because the smaller atom will attract the electron more strongly. So put that because and therefore here. So if this is how the size change across the period and down the group, you know for the electronegative trend it should be the reverse, right? Correct? Yes? Okay, so now look at Na and Al. Where are Na and Al? I mean all the way to Al in the periodic table. They are here. Al, Sip, Cl, Al. We are going from left to right, right? That means we're seeing an increase in electronegativity. Okay, increase in electronegativity. And because oxygen has a pretty high electronegativity, let me look up the electronegativity table here. You don't have to memorize this value, they will give it to you. But just a moment. So we have, right, okay. So we have this diagram in here. So let me just cut this out. And we have, when you take a look at this, focus on the oxygen. Oxygen is here. Oops. So oxygen is here. It has electronegativity equals 3.5. And all these atoms, they are trying to form a bond with silicon. Okay, so we have Na here, trying to form a bond with oxygen, and chlorine here trying to form a bond with oxygen. Look at the difference in electronegativity. When Na forms a bond with oxygen, all the way to like SO2, Cl2O. What's the electronegativity difference between the metal and oxygen? So let me write down. Oxygen is 3.5. Sodium is 0.9. Magnesium has electronegativity 1.2. Can you tell me what's the difference between these two? It's 2.6. And this is 2.3. What you're seeing as you continue doing this to SO2 and ClO2 is that the difference, does it become smaller or does it become larger as you go from left to right?
Smaller.
It becomes smaller. And actually, this is one way to define the nature of the bond. The smaller the difference in electronegativity, the more covalent the bond is. Okay, so put this second point now. This has a difference of 1.0. This has a difference of 0.5. We call this the electronegativity difference. So you can see that on the left, these are large electronegativity difference compared to these ones, right? These have small electronegativity difference. Large electronegativity difference means the bond is ionic. Okay? Small electronegativity difference means the bond is covalent. So that means the bonding character changes from ionic to covalent. Okay? Yeah, you can think of it this way. When you have two atoms with very different, well, I mean when you look at these two numbers, they look very different, right? One is 3.5, it's almost 4 times the difference here, you see. That means oxygen attracts the electron more strongly than sodium. This is why when sodium and oxygen are to form bonds, sodium would give up an electron to oxygen. Because think of it this way, I'm oxygen. Me having 3.5 as the electronegative value means I attract electron more strongly than sodium. So therefore I will steal an electron from sodium, resulting in the formation of ionic compound. What happens when two atoms have very similar electronegativity? Okay, it means they both attract electron equally strong, right? Do you remember what kind of bond is this when two atoms attract electron equally strong? We call that covalent bond. So you see, these two atoms, they attract electrons equally strongly. So we have a covalent bond in between. Okay, but yeah, if this is too much for you, just know that large electronegative difference means ionic bond. Small electronegative difference means covalent bond. Okay? Right. So that's the first thing we can compare. The second thing we can compare is the acid-base characteristic. Okay, so acid-base character. So metal oxides, they are basic. Okay, so metal oxides, they are basic. But this doesn't apply to Al2O3 as there's another name given to this special oxide. This is amphoteric. Amphoteric means it has both acidic and basic property. That's a very interesting oxide, and they will definitely ask you the equation also. Can you put a star here? So amphoteric. Amphoteric means exhibits both acidic and basic behavior. So in biology, you may have heard of the word amphibian. Here you have a similar word, amphoteric. It means it can do both acid and base reaction. Okay, so it can exhibit both acidic and basic property. This is a key word. Okay, you can do both. And then we have the acidic oxides on the right. So silicon oxide all the way to Cl2O7, these are acidic. Okay, so we'll look at this now. What are basic oxides? Basic oxides means they can dissolve in water to form a solution with pH. Is it greater than, equal to, or lower than 7? What does basic mean? Basic means it has a pH greater than 7. Okay, so put down why are they basic. Okay, so basic because of 3 things. So because, number 1, they react or they dissolve in water to form basic solution. Okay, so basic means pH is greater than 7. Yeah, basic solutions. The second reason why we call them basic substances is because base reacts with acid, right? So they react with acids. Okay, this is why they are basic. So we are looking at different definitions of a basic substance. You can call something basic when they dissolve in water to form a solution with pH greater than 7. You can also call something basic when they react with acid because they react with acids to form salts. Okay, so to form salts, so react with acid. So we will look at them in detail shortly. But can you put down amphoteric here? Why is it amphoteric? It is amphoteric because it reacts with both acid and base. So this is amphoteric because it reacts with both acid and base. You know, we call this a basic substance because it only reacts with acid. But now we are calling Al2O3 an amphoteric substance because it reacts with both acid and base. Okay, you see that basic substance can only react with acid. Amphoteric substance can react with both. It follows that acidic substance can only react with base. They cannot react with acid because they are already acidic, okay, on the right. So can you put down acids? Why are they acidic? Because of two reasons. So acidic because they dissolve in water to form a solution with pH lower than 7. In fact, they can all dissolve in water to form acid. So in water to form acids with pH lower than 7. And why do we call them acids? That's because they react with base. Okay, I can think of a question, okay, that might ask you, okay, in the essay exam. How do you tell apart a sample of MgO and Al2O3? So let's say on the table, you are in the lab right now. You are presented two unlabeled beaker, inside of which you see white powder. They are both white, MgO and Al2O3. Based on what you see in here, in this chart, you can just look at property number 2. You don't even need to look at the ionic and the ionic character or the covalent character. Can you tell me what is the acid-base nature of these two oxides? This is a basic oxide. This is a this is an amphoteric oxide. Yeah. So that means what can I add into these two substances to tell them apart? Should I add a base into these two substances to tell them apart, or should I add an acid into these two substances?
Base.
We should add
Base.
a base. Why? Because, can you put it down? MgO. Yeah, for this question you need to think. Al2O3 is amphoteric. That means it can react with both acid and base. MgO is basic. That means it can react with acid. So can you construct this table on the right? Okay. Can they react with acid? Can they react with base? Let's put a tick or a cross in these boxes. For Al2O3, which of these does it react with? Both. So tick tick. What about MgO? Only acid. Would you add something that both substances can react with to tell them apart? No. For example, if I want to tell apart you two, do I say, oh, let's look for a human being? No, you won't look for something in common, right? Yeah, between two samples. You will look at something that is different. You will add a base because you know only one substance will react. It's Al2O3. You don't want to add acid because both will react. Do you get my question?
No.
Yes. This is how they can set a question on the acidic, basic, and amphoteric behavior. So can you turn it into a question and write down the answer? So question. Suggest what you can add to MgO and Al2O3 to tell them apart. Okay, so to tell them apart. The answer is a base because they react differently towards a base. Okay, so the answer is a base, e.g. NaOH. Only Al2O3 will dissolve in base. Okay, will react with or dissolve in base. MgO, it will appear like it's not reacting at all. When you throw a base in, nothing happens. Okay? So in a base. Is this clear? Okay? Now the hard part. Okay, so I know all of you are falling asleep. Okay, so some equations now. Okay, let's write some equations. Okay, we're going to prove that basic oxides, they are indeed basic. Okay, on the next page, equations. Okay, so writing equations. So to show that the Na2O and MgO are basic, we do two things. So to show that Na2O and MgO are basic, we can either react them with water or with acid, because that's what a basic substance means. So a base can dissolve in water to form an alkaline solution. So dissolve in H2O to form hydroxide ions. Right? This is the first property of base. Okay? The second property of base is that they react with acid. So we can use these two properties of a base to write equations. So starting with number one. Okay, how do you show that Na2O is basic using the first equation? Well, we say Na2O plus H2O. Do you remember the word equation? When an oxide reacts with water, what will be formed?
NaOH.
Yeah, meaning a hydroxide. Okay, so can you put down hydroxide here? Yeah, so you have NaOH. And NaOH, is it a strong base or weak base?
Strong.
Strong base. Okay, so put down it is a strong base. So it will dissociate 100% into
Hydroxide ion.
and sodium ion.
Oh.
Oh yeah, sodium ion and hydroxide ion. What about MgO? Can you write a similar equation here? When magnesium oxide reacts with water, what does it form?
MgOH2.
MgOH2. You remember that OH is 2 is 1 minus charge and Mg is 2 plus charge. So it's MgOH2. But is magnesium hydroxide a strong base or weak base?
Weak.
It's a weak base. Do you remember the table of strong acid, strong base, weak acid, and weak base? If you don't remember it, let me remind you now. So you have strong and weak. So strong substances, they dissociate completely. Weak substances, they dissociate incompletely into ions. And this table, you have to memorize it in the acid and base chapter. So write it down, please. So for strong acid, you have all mineral acids, HCl, HNO3, H2SO4. That's it. That's not a lot to remember, right, from just this box. Strong base, you have all group 1 hydroxide. Okay, all group 1 hydroxides and barium hydroxide, strontium hydroxide. That's it for strong base. For weak acid, this includes all carboxylic acids. What is the general formula of carboxylic acid? But that's the function.
Oh wait, no.
CnH.
2N plus 1 COOH.
Yes, okay. When you say COOH, that's the functional group. No difference between functional group and the general formula. Okay, so all carboxylic acid, and then H2CO3, H3PO4, H2SO3. Finally, weak base, only 2. Okay, so you have ammonia. What's the formula of ammonia? NH3, and all amines. All amines. Okay, things with NH2. Okay, so for example, CH3NH2. Okay, yeah. Oh, by the way, you know when you go to the fish market, you smell fish. Okay, you're actually smelling the amine. Okay, amine are formed when fish decompose, when they rot. They give off that fishy smell. Some people find this very off-putting. Okay, yeah. So the amines. So now we can use this table to figure out whether you can say that if bases are not strong, If you have a base that is not strong, it will be weak. Okay, so for other,
The base not strong.
so if a base is not strong, it will be weak.
Makes sense.
So you can say here magnesium hydroxide is not barium hydroxide, right? It's not strontium hydroxide, right? So you can maybe add MgOH2 in here. It's not a very strong base. So how will you write the second equation then?
Not weak and strong.
No.
So what is the arrow we should put for weak base then? It should be a reversible arrow. Okay, it will form magnesium ion and 2 hydroxide ion. So this is less than 100%. You have a weaker base. So that means when I put sodium oxide and magnesium oxide into water, which of these oxide will produce a higher pH solution? Which would produce a lower pH solution? So let's just say I have a test tube in here with water, and I'm putting sodium oxide and magnesium oxide into both of them. Yeah, each of them I should say. Which would produce a higher pH solution? The first one or the second one? The first one. That's because according to the equation, which one will produce more OH minus ion? Sodium hydroxide. So can you put down more? And can you put down less? Why are there less? Because of the dissociation. 100% means it will dissociate completely. No NaOH will be left. All will be split. Okay? And when you see less than 100%, it means you will have very few OH minus. So can you draw many OH minus ion here? And just one. So this has a higher pH as a result. Okay? This has a lower pH. Yeah. So I know suddenly we are switching back to pH, but you should know that pH can be high or low. So you have high pH or low pH. Low pH means the H plus concentration is it high or low? When you have low pH, means the H plus concentration is high. I remember it this way. This is the H plus concentration. This is the hydroxide ion concentration. Where they become equal is neutral. When you have low pH, it means you have more H plus than you have OH minus. When you have high pH, it means you have more OH minus than you have H plus. Yeah, so which one has more OH minus? This one. Yeah, so no wonder Na2O or the resultant base, NaOH, has a higher pH. Okay? Yeah, you need to integrate it, okay, with what you learned earlier. So this is part 1. So this is part 1. What about part 2? How can you react base with acid? Okay, so here this is equation part 2. Do you remember, what was that? Okay, the removal of sulfur dioxide. Do you remember learning about sulfur dioxide in the fossil fuel chapter?
Yeah.
Sulfur dioxide is a pollutant. What are some ways to reduce scrubber? What is the formula or the name of that solution used to scrub SO2?
Wait.
Where's that?
It's
Don't know.
calcium hydroxide. Calcium hydroxide. It's a base, okay? So we can react sodium oxide and magnesium oxide with acidic substances like SO2 or CO2, and that will form a salt. As you remember, that a base will react with acid to form salt. Okay, whether there is water, it depends on whether there is, hydrogen. There's no hydrogen, so there's no water. Okay, so you get a salt. What is the formula of the salt here? It's Na2SO3. Just SO3. Because you see, you don't have enough O to make SO4. There are only 3 O's in here. Can you see?
Have hydrogen than have water.
If you have hydrogen in the base, like hydroxide,
Right?
yeah,
How
then
about in acid?
sorry.
How about in acid?
How about in
Like
acid?
you remove HCl.
Oh, if it reacts with HCl, yes, then you can also have water. Yes, okay. But here we don't have any hydrogen in here, so no water. Yeah. What about the second salt? MgCO3. Okay, so this will be the salt. So we have 2 definitions of a base. When we say something is basic, it can mean two things. Number one, it can mean that the basic substance dissolves in water to form an alkaline solution with a higher pH than 7. It can also mean that the basic substance reacts with acid to form salt. Okay? So these are the two definitions of a base. One is that base can dissolve in water to form an alkaline solution. Second is that a base reacts with acid to form salt. Okay? So now we need to show, this is the hardest part. How do we show that Al2O3 is amphoteric? Okay, so pay close attention. So to show that Al2O3 is amphoteric, what do we do? Remember, amphoteric means it is both acidic and basic, right?
Yeah.
Yeah, when aluminum oxide, this very strange oxide, reacts with acid, it becomes Al3+. When aluminum oxide reacts with base, it becomes a very complex ion, AlOH4 bracket minus. Okay, so this is tetra, or the one on top, I don't think I need to tell you the name. This is aluminum ion. Everybody should know this. But this one is tetrahydroxyl aluminate. Okay, and don't worry, I rarely see this word being asked. Okay, but the formula you certainly need to know. AlOH4 minus. Let's write an equation. Okay, so here's it. Let's work on this together. So question: write the equation for the reaction between Al2O3 and H2SO4.
What?
Right. Yeah, so tetrahydroxyl aluminate. Yeah, so the name is not as important as the formula. The formula is very important, this one. So when you have Al2O3 reacting with H2SO4, they will ask you to complete the equation. And then when they react Al2O3 with NaOH, which is the base, they will ask you to complete the equation. And I'm here to show you how to balance these two equations. The first one everybody should know. The first one is just a normal acid-base reaction. What are the salts and the water? What are the products? Yes, Al2SO4. I think the first one, everyone knows how to figure that out. So just put down Al2 bracket SO4 and H2O. How do you balance it? 3 how many? 3 what? 3 what?
3 H2.
3 H2SO4 and how many water? 3, yeah, so you get 3 H2O at the end. Okay, that's the first equation. Very easy, right? It forms Al3+. So you can see Al2SO4 is actually 2 Al3+ and 3 SO4 2 minus. So this is aluminum sulfate. What about this one? Can you put 2 stars here? Yeah, oh, but the way I remember it, I'm not sure how you memorize it, okay? But the way I remember it is I write Al2O3 plus OH minus becomes AlOH4 minus first. So can you copy this equation? I will show you how to figure out the product. But first, you need to remember these 3 substances. Oh, yeah, okay. Yes, and then you need to. Yeah. Okay, great. Yeah, you can go to.
What's your fourth then?
Yeah, why are there 4 of them? Because I want to show you how I get these products. First of all, you balance the Al. Okay, so balance Al. Do you see 2 Al here? And there's only 1 on the right, right? So we balance the Al by putting a 2 here. Okay, so step 1, balance Al. Okay. Step 2, balance the charge. Okay, do you see 2 negative charge on the right? Yes, 2 minus, 2 negative, 2 negative. How many negative charge on the left? 1. So you put a 2 here. So step 2, just to balance the negative charge. Okay, so balance the number of negative charge species. Okay. Finally, well, we only need 1 more equation then. Can you tell me which side is deficient in hydrogen? And by how many? How many hydrogen are there on the left?
2.
2. How many hydrogen are there on the right? Be careful.
8.
8 or 4?
8.
8. So 2 on the left, 8 on the right. So which side is deficient in hydrogen? Left by how many?
4.
6.
6.
8 minus 2 is 6. Okay, so we then add water. We add, how many water can make up for 6 hydrogen?
3.
3. Done.
No.
Done. It's done. Trust me, it's done. It's balanced. Okay, so step 3 is to balance.
Oxygen is done.
Oxygen is automatically balanced. You can
Oh,
check.
okay.
Okay, so you have 2 in here. Let's check. This has 3 O.
8.
This has another 3 O. This has 2 O,
Oh, okay.
which makes up 8 O. This has 8 O. It's balanced.
Why the 2? So the 2, the yellow 2.
I mean, right. Yeah, the yellow 2. Yeah, sorry. Okay, so you have this. But then still, this is not what the question wanted, right? How do we write an equation for Al2O3 and NaOH? Do you see that for every NaOH, we need 1 Na plus, right? So to make 2 OH minus 2 NaOH, we need to add 2 Na plus to both sides. Okay, so can you add finally 2 Na plus to both sides? So let me add 2 Na plus and 2 Na plus. Okay, it's just like when you do math question, when you have x, I don't know, minus 3 equals 4, you will need to do plus 3 on both sides, right? Yeah, because that's what equation means. You need to add the same thing to both sides to make it right. Okay, so finally, how do we turn this back into the product? Can you see that these two would combine to form NaOH? You have 2 NaOH. And can you see that these two can combine to form this very complicated looking thing? 2 NaAlOH4. And don't forget, free water on the left. Okay?
Why the left?
Yeah, okay. Well, it's better that you remember this way than to just memorize the equation. I mean, can you memorize this equation?
Yes, probably.
I cannot. I don't memorize the equation. I just work it out from scratch, like I just did. You don't have to memorize any equation for this part. You see, I did not memorize this equation. I just work it out from the beginning. You need to remember the reaction and product though. That's all you remember. Okay? Yeah, so remember the steps. Okay, oh, I forgot to write down. Balance the number of hydrogen. Okay? So if you think, oh, I'm better off remembering the equation, well then, so be it. Okay? Remember these two equations. When they ask you what will happen when I add acid to aluminum oxide and when I add a base into aluminum oxide. In both cases, aluminum oxide dissolves. Can you write down the state symbol? This is a solid. Okay, let me write it in red. This is a solid, but these are both aqueous substances. Okay, so that means this is a very unusual oxide in that it dissolves in both acid and base. Okay, if you have a basic oxide, it will only dissolve in acid. If you have an acidic oxide, it will only dissolve in base, but not for amphoteric oxide. Amphoteric oxide dissolves in both acid and base. Okay, so you see it dissolves. And here it dissolves. Okay, is this clear? Yes. Now we turn to the acidic oxide. Okay, so this is basic oxide on the left. This is amphoteric oxide on the right, and then we have acidic oxide on the back. Okay. Do you know what we should use to store sodium hydroxide in the lab? Should we use glass to store sodium hydroxide? Have you seen sodium hydroxide stored in glass bottle? No. Why not? Because it will react with sodium hydroxide. Okay, the glass. This is what we come to next. To show that SiO2, P4O6, SO2, Cl2O are acidic. You need to write equations to show that they are acidic. Okay, for SiO2, let me write down. SiO2 is insoluble in water. So you cannot write an equation between it and water, but it will react with glass. SiO2 is glass. It will react with sodium hydroxide. Okay, so it is insoluble in water, but reacts with base. So P4O6, SO2, Cl2O, they are soluble in water and they react with base. Okay, so and they react with base. So you need to remember these two separately. Okay? Okay, so let's take a look at the first reaction, SiO2. So SiO2 can react with OH minus to form SiO32 minus. Do you remember learning this ion in form 4? No. But let me tell you, carbon and silicon, they are in the same group. So this is a very similar ion to carbonate ion. Do you remember CO32 minus ion? CO32 minus. C and Si, they are in the same group. So this is a very similar ion to that. So how do we balance this equation? First, can you tell me how many negative charges are there on the right?
2.
Negative.
2.
2. So how many negative charges on the left? 1. So we can put a 2 here to balance the negative charge. But this is unlike the redox equation balancing. This is unlike redox equation balancing. We balance the number of negative charge species. Now, what do? We balance water, okay, or oxygen, you can say. So which side needs oxygen now? Right side needs how many?
Oxygen?
How many oxygen are there on the left?
4.
4. How many oxygen on the right? 3. So how many water can I add to? 1. So we add 1 water, and it's done.
Oh, yeah.
The equation is balanced. Okay. So balance the number of oxygen. So why do we need this equation here? This equation shows that SiO2 is acidic. Okay? Because what does OH minus represent? It represents base, right? It represents base, right?
Yeah.
So when acid reacts with base, it forms a salt and water. Okay, so this is the salt and this is water. So if you're asked, what does this equation show? This equation, you say, it shows that SiO2 is an acidic substance. Because if it were not acidic, it cannot react with base to form salt and water. Right? Yeah, so can you put down the very small conclusion here? The conclusion we can draw from this equation. SiO2 is acidic because it reacts with base to form salt and water. Okay? So it reacts with a base to form salt and water. Okay? Now, this brings us to why you shouldn't use glass to store sodium hydroxide. Okay? So why you shouldn't use glass. What is the formula of glass? The chemical present in glass is SiO2. Do you know that
Yes.
glass is SiO2?
Of course.
Okay. Then yeah. So why you shouldn't use glass bottle to store sodium hydroxide? Because it will etch it. It will dissolve the glass. If you put the sodium hydroxide in glass bottle for too long, it will dissolve. It will create a hole in the glass bottle. So can you draw this? So this is glass. It's SiO2. When you store sodium hydroxide in glass bottle, so this is NaOH. The OH minus, they will attack. Okay, so they will attack the glass. Okay, by this equation. Can you put down the stay simple? SiO2 is a solid, but silicate is an aqueous substance. What does that mean? When you turn a solid into an aqueous substance, it means it has dissolved. Okay? Yeah, so solid dissolves Okay, right. So you can put down at the end what will happen. There will be a hole. Okay, like in here. Yeah. So why is there a hole here? This is because silicate, okay, is formed and it gets flushed out. Okay, so this is SiO3 minus is soluble. So there will eventually be a hole in the glass bottle. So you shouldn't use this to store. Can you suggest an alternative then? If glass cannot be used to store sodium hydroxide, what is the very unreactive material that we see in everyday life? Is plastic. Yeah, okay, so plastic. So we can use plastic. You know, plastic, they are resistant to attack by acids and alkaline, right? But then should you use polyester? Should you use polyester or polyamide to store sodium hydroxide? Polyester or polyamide? Should you use polyester or polyamide, which is also a type of plastic, to store sodium hydroxide? Yes or no?
No.
Will there be a reaction? No, you shouldn't react. You shouldn't store it in polyamide. Why? Do you remember a reaction called alkaline hydrolysis? Yeah.
I forgot
What is
everything.
alkaline hydrolysis?
But what is alkaline hydrolysis?
Then use the keywords.
Do you remember alkaline hydrolysis?
Yeah.
It means you are breaking down an ester with hydroxide.
Yeah.
Oh, okay.
So should you use a plastic bottle made of ester
No.
to store sodium hydroxide?
No.
No, the sodium hydroxide will break it. It will break it. Okay, yeah. So you need to relate this back to many pages ago. Okay. Yeah. So it will just dissolve. So finally, can you put down P4O6, P4O10? How do these react with water? So when P4O6 reacts with water, it forms an acid that you may have heard of. Maybe you have heard of its brother. It's H3PO3. The brother is H3PO4. Okay, this is phosphorus acid. Phosphorus, not phosphoric. Phosphoric is H3PO4. Okay, and then you have H3PO3 to be a weak acid. So it will dissociate completely into, I know on the textbook it says PO3 minus, but it's actually not very true. So you have HPO3 1 minus, which will then dissociate into PO3, so HPO3 2 minus, which will then dissociate into PO3 3 minus. Yeah, so the textbook just write these two. But in the process, you actually have to give up one H plus one at a time. You cannot give up all H plus at the same time. Okay? So you will have, you can say it only dissociates very slightly. So this is a weak acid. So weak acid. So does it have a very high pH or very low pH if this is a weak acid? Higher pH than strong acids like HCl of the same concentration. Okay, so therefore they can easily turn it into a question like this. Oh, you have in a jar 1 molar HCl and 1 molar H3PO3, and you stick a pH meter in, and then you're asked to compare the pH value. Which one should have a higher pH value?
HCl.
Higher pH value.
HCl.
Yes,
So
H3.
trap.
Okay, yeah, so this is pH. So you have a higher pH because it has less H plus due to it being a weak acid. Okay? Is this clear? Yes. Okay, so know that this is strong, meaning it dissociates completely, and this is weak. It means it dissociates incompletely. So the strong acid, it will dissociate completely into H plus and Cl minus. The weak acid, it will dissociate very, very slightly into H plus and H2PO3 minus, which will dissociate into HPO3 2 minus, and then finally PO43 minus. Yeah, so this is much less compared to this. Okay, so you have more because of the irreversible nature. You have less. I know you see 3H plus on the right compared to just 1, but you have to consider also the reversibility of the reaction. Yeah, so together they will still make for less H plus. Okay? Tricky. But the other reactions, they are similar. Okay. By the way, what do you think this is called? P4O6. What do you call CO2 first?
Carbon dioxide.
The name. Carbon dioxide. Okay. If you have not two
Tetraphosphor.
tetra
Tetraphosphate.
tetraphosphorus hexoxide. Hexoxide.
Why?
Because you have two vowels. Normally you would call it hexoxide, but because when you have two vowels next to one another, you drop the first one. You know carbon monoxide, right? Have you ever questioned why it's not called monoxide? That's because you have two vowels. If you have two vowels, you need to drop the first one.
English lesson.
No, this is not English lesson.
It's
But
more than
in chemistry, if you have two vowels, it's difficult to pronounce. Think about monoxide.
phosphorus.
Monoxide. Is it easy to pronounce or is monoxide easy to pronounce? Monoxide. Same thing here.
I
Hex-
choose chemistry because I think it's lot like less like languages.
Yeah, there's math, there's English in chem, as you see now.
Why? Why do you exist?
Right? Well, you can just refer to it by name. I'm just worried that they will show you tetraphosphorus hexoxide and ask you to write the formula. At least you know tetra means 4, hexa means 6. The reason why you don't see an A here is not because there's a typo, but because it's difficult to pronounce. Okay? So the other two is similar. So you have SO3 plus H2O.
Less languages that possible.
So this forms sulfurous acid.
So
It's not sulfuric, but sulfurous. It has one oxygen short, you see, compared to H2SO4. Okay? You can't have H2SO4 here because you see there are only 3 O on the left. I would really want to make it H2SO4, but I cannot, as there are only 3 O on the left, do you see? Yeah. So, and then sulfuric acid is unlike sulfuric acid. It is a weak acid. So H2SO4 will dissociate incompletely. Maybe this is too hard. You can write 3PO. So 3H plus and PO 3 minus. And here you can write 2H plus SO3 2 minus. So because it is a weak acid, it will also not have a very low pH. It will have a relatively high pH. Sulfurous acid, okay? And then we have Cl2O. Can you try to name Cl2O? I think you know SO2. SO2 is sulfur dioxide. Dichlorine monoxide.
Why?
Yeah,
Why?
So, but yeah, you know for the first element you don't need to change the name. Yeah, so it's sulfur. You did not call it sulfoxide dioxide, right? You call it sulfur dioxide. But then for Cl2O, you have 2 chlorine, so dichlorine monoxide. Not monoxide, but monoxide. I'm just worried that they give you the name and ask you the formula. The formula is the least you need to know. You must know the formula. That's part of this chapter, okay? When you react this with H2O, you get an acid that you will find in bleach, okay? So it's HClO. They may ask you to draw HClO. Can you draw HClO now? Yeah, so it's either HClO or HOCl. It means the same thing. But the atoms, they have to be in a particular order.
Oh,
It is similar to water.
yeah.
If you know how to draw water, you know how to draw HOCl or HClO. What does water look like? Water looks like this, right?
Yeah.
So
OAH.
it will be HOCl. Okay, so you know Cl is from group 7. Okay, but it will still only use one of the electron in bonding, just like hydrogen. So HClO and H2O, they have the same shape, okay, and this is V shape. So HClO, yeah, this is hypochlorous acid. colorless acid because they all dissociate reversibly. Yeah, or you can write OCl minus, doesn't matter. So here you can write HOCl as well. So it really doesn't matter. You can write HClO or HOCl. It is again a weak acid. So these are not in the same league as HCl, H2SO4, and HNO3. They are very weak acid, all of them. All of these. They're very weak acid. So can you add this back to our table? In here, we can now add a few more acids into here. So we have HClO or HOCl, and then we have H2SO3, we have H3PO3, yeah, etc. Right. So is this part clear first? The equation. Yeah, you need to remember these three equations. Okay. So now let's move on. So we have this one and this one here. So this part is done. Okay. We can then look at.
You should take a
We're
look.
done with how many
Yeah.
trends? Oh, that was a lot. That
Yeah,
was
that's a lot. That's a lot. Okay. So we are halfway through. Transition metals
kind
now.
of halfway there.
Yeah, transition metal is the last book in this chapter. Yeah, I mean the last topic in this chapter, I should say. Okay. Yeah, so we have transition metals next.
아이고.
Where are transition metals? Where are they found on the periodic table? They are found between which two groups?
Metals.
Group 2 and group 3, yes, okay. So they are put down
와.
metals
Wow.
found between group 2 and group 3. So let's draw out a periodic table and show where you can find the transition metal. So here, so you have group 1, you have group 2, and then a long way before you can see group 3, and then group 4, and then group 5, and then group 6, and then group 7, and then we have the last group here, group 0. Okay, so group 0 is a little bit longer because it has also helium in the first period. This is where you find the transition metals. Okay, so they are positioned between group 2 and group 3. Okay, so you have group 2, 1, 2, 3, 4, 5, 6, 7, and group 0. So this is the group. So they are found here. Right. So what are some unique properties of transition metal? And what do you call the other metals? So group 1 and 2, if you remember the name, group 1 is the alkali metals. Group 2 is the alkaline earth. Yes, alkaline earth. And the other groups, they also have got names, but you only have to know group 7 and 0. Group 5 and 6, they also have got names, but don't worry about them. So alkaline earth metals. So what do we call these three blocks of metals? Group 1, group 2, and group 3, we call them the main group metals because they have a group number. Transition metals are those in between group 2 and 3. They are not called main group metals. They are transition metals as they do not have group number. So transition metals. Okay? They are different groups of metal. Okay? They are very different. Let me give you an example. A sample main group metal would be sodium, and a sample transition metal would be iron. So what can you think of? Okay, when I ask to name some differences between sodium and iron, which one is harder?
Iron.
Iron, right? In general, transition metals, they are harder. And main group metals, they usually are less dense. They are less dense. Okay, do you remember seeing, maybe it's a long time already,
Sodium getting
do you
cut with
remember
a knife.
seeing sodium in the lab? Yeah, they are stored in oil, okay? And when you look at lithium, it's even more dramatic. You can see they're incredibly low density. It's only 0.5 grams per cm
It's
cube.
upside. I thought that was upside down.
Oh, you thought it was upside? No, it's actually floating in water.
No, it's just floating.
Oh, and by the way, this is not water.
That's-
If this were water, it would have exploded.
If it was water, it'd be fun. Very fun.
It will, yeah, okay, maybe that's the last thing you will see, okay,
Oh
if you put in
my
water.
God,
And
what a
You can see that all these metals, maybe it's too small for you to see, but the density is smaller than 1, meaning it's lighter than water. But you cannot put it in water as it will explode, okay? So, can you put down some features? They are less dense, generally, and then transition metals, they are denser. Main group metals, they are softer. Remember how we can cut main group metal with knives, right? You know you can cut main group metal with knives.
Yeah.
Yeah, you cannot do that with iron. Okay, so they are softer, and transition metals, they are harder. What about the charge formed by the ions? Can you predict the charge of group 1, 2, and 3 ions?
Yes.
Yes, because group 1 will form +1, group 2 will form +2, group 3 will form +3. Their charges, okay, are fixed. So forms ion with fixed charges. If it's group 1, it must be +1. Group 2 must be +2. No other ions formed by one particular metal. Transition metal, not so much. They can form ions of variable charges. Like iron. What are 2 possible ions formed by iron?
Fe2+.
2 plus and 3 plus. Okay? Which brings us to the next point. Which of these metals will form colored compounds? You mean transition metals in general. Okay, so they generally form, on the left you can write down, white compounds. Okay, so they form white compounds, which would then dissolve to form colorless solution. And transition metals, they usually, okay, not always, so usually form colored compounds. So colored compounds and colored solutions. Okay? And last but certainly not least, transition metals, they have catalytic property. So you remember catalysts, right? So catalysts can speed up reaction without being used up. Okay, they will not get consumed. So main group metals, they have no catalytic property. They cannot speed up reactions. Okay? Can you name a few catalysts? Can you name a few catalysts? Al2O3. What is Al2O3 a catalyst for?
Oh no.
Wait a second, sir. Wait a second.
I think I wrote it down, but I don't
No,
know.
Something in organic chemistry.
Well, you narrow it down by a lot, okay? So, narrow it down. Okay, you're right. But do you remember the name of that reaction? It starts with letter C.
Condensate.
Cracking.
Cracking.
Oh.
Cracking uses aluminum oxide or silicon oxide as the catalyst. Okay, but then I think aluminum oxide is not a very fitting example here because aluminum is not. Platinum is the catalyst for
I don't know.
For
hydrogenation
hydrolysis.
of alkenes.
Alkene to alkene.
So write this down. So ET, when you turn alkene
Yeah.
into, so this is addition with platinum. Platinum is a transition metal. You get alkane, okay? So you get alkane here. What about, remember Haber process?
What?
Haber process in the equilibrium chapter that produces ammonia. I think we talked about this many lessons ago. Let me find. Haber process.
What is that?
What is that?
Oh, no.
What is that? Well, you saw it here. So Haber process, let me show you. Haber process uses the catalyst. Where did I put it? I think I put the catalyst somewhere here. Okay. Oh, if I haven't, I'm putting it down now. It's iron. Okay. So you will need iron as the catalyst. And iron is.
It's a child.
Yeah, I think iron is a transition metal. Okay. So can you put this in here? So you have hydrogenation. Remember the name if you don't already know. Hydrogenation of alkene. We have also what? Haber process. Okay, so Haber process uses iron. What about catalytic converter? Do you remember the reaction catalyzed by catalytic converter, which you learned in Form 5? It turns carbon monoxide and nitrogen monoxide into carbon dioxide and nitrogen. Okay, so put down catalytic converter. Yeah, I try to use examples that you have learned before, okay, rather than introducing you new examples. So Haber process turns nitrogen and hydrogen into ammonia using iron. Okay? Catalytic converter turns nitrogen monoxide and carbon dioxide into harmless carbon dioxide and nitrogen using platinum. Okay? So if you have to guess platinum. Platinum can do a lot of things. Okay? So if you forgot about the name of catalyst, you can guess like platinum. So they have catalytic property. Can you name some colored compounds of transition metal? For example, one you learned in Form 4. What can you use to test for the presence of water? There are two compounds.
Anhydrous copper sulfate.
Yes, anhydrous copper sulfate. One more. Anhydrous cobalt 2 chloride. Okay. Yeah. So can you put down copper sulfate is blue, cobalt chloride is pink. So cobalt chloride is pink because of the cobalt ion. Copper sulfate is blue because of the copper 2 plus ion. So they can form colored compounds. And they can form ions of variable charges like Fe2 plus or Fe3 plus. Okay, so iron can form 2 plus or 3 plus. Yeah, this is to show you that, well, yeah, they do show variable charges. They do form colored compounds, but not the word usually. Can you give me some counter examples? Are there any transition metals?
Manganese.
Manganese is actually colored.
It is?
It is.
Manganese. What's the other one that starts from M?
There's not a metal that starts with N that forms colorless compounds.
M.
What about silver? Do you remember silver nitrate?
Silver is
Is silver nitrate colored or colorless?
colorless.
Colorless. So that means they don't always form colored compounds. Can you put down some counter examples? Okay. Silver and zinc, they are transition metal ions that are colorless. Okay. So they are not always colored. So these are the counter examples. But most of them are colored. So we will now look at the electron arrangement, okay, of the transition metal. Okay, so the good thing is you don't have to know how they are worked out, okay. But then we'll first look at the properties, okay, of transition metals. So first, we have the high melting point. So let me finish this first. So higher melting point and strength than main group metals. So let me start with calcium. Okay. Okay. Let me start with calcium. Calcium has atomic number 20. Okay, so scandium has atomic number 21. So this is a main group metal. And can you tell me what's the electron arrangement of calcium before I wrap this up? What is the 2AA2? Yes, and then the transition metal scandium is, you don't have to know this because this is beyond the SE. I said you only need to know up to 20, right? Yeah. So it's 2892. It's 2892. Yeah, you don't have to know why this is 2892, but let's just say you know now you're given that it's 2892. The reason why main group metals they are softer is because they can only use the last shell, okay, when they delocalize the electrons. But for transition metal, they can use both the electrons in the outermost shell and the second last outermost shell. Yeah, so therefore, which has more electrons?
The last one.
the scandium, the transition metal. So can you put down, they have more delocalized electrons. Do you remember metallic bond strength depends on the number of delocalized electrons, right?
Yes.
Yeah, so this is why they are stronger. Is that clear?
Okay.
Okay, so we'll pick up from here. Okay, and let me upload this onto Google Classroom. Okay, we have to